Hi, I am Takuto Nakamura, the main presenter of this project. Other authors are Daichi Saito, Erwin, and Professor Hideki Koike, all from the Tokyo Institute of Technology. We will introduce our project, Actuated Club. This system is introduced for training accurate golf swing. It actuates a club to correct club angle and improve trainings. In order to realize the system, we use an ungrounded force feedback and the motion prediction of a golf club. For the background of this project, we first introduce golf swing. In a golf swing, trajectory and the club angle affect the direction of the hit ball. First, trajectory affects the curve direction. For example, if a golf club is swung with the orange trajectory a ball will follow the orange curve. Also, club angle affects injection direction. For example, if a club is tilted like the right figure, a ball will be injected to the right. However, most beginners cannot control a club well during swing. Therefore, it is difficult to hit the ball in the intended direction. To improve their skill, they try swing training repeatedly. Considering ideal swing training, we think it requires swinging a club with the correct trajectory and club angle every time, because users learn motion from the both correct swing and incorrect swing. Therefore, they reduce the number of incorrect swings to prevent negative learning. To realize ideal training, multiple swing training methods are proposed. Popular method is a verbal advice from a coach, but the expression of a verbal advice is limited when, where, or how to move. In HCI research field, auditory and visual feedback methods are proposed to tell more detail. However, users need to understand those feedbacks, and it is difficult to correct motion during swing. Manipulating the user's body with a robot arm can correct motion during the swing. However, this method needs cost and limits the user's range of motion. Therefore, we decided to use an ungrounded force display to correct swing. This method presents force sensation without the device connected to the ground and does not limit the range motion. Asymmetric vibration induces force sensation by holding vibrator. However, this method cannot move a heavy object, such as a golf club. Electric muscle stimulation presents force sensation to the body, but there is a safety issue to use for a long time. Therefore, we selected the gyro effect as ungrounded force display. Gyro effect is a phenomenon that generates torque when the flywheel is rotated by external gimbals. This method can generate strong torque depending on parameters of flywheel, such as radius, weight, spinning speed. However, this method also has an issue. It has a delay from command to generating torque. To cope with this delay, we use motion prediction. There are two major methods of motion prediction. One method is an mathematical model-based method. This method formulates and predicts movements, such as predicting a bouncing ball. However, this method is difficult to formulate golf swing due to human habits. The other method is a deep learning-based method. This method learns pre-recorded motion data and predicts motion, such as volleyball and ping pong ball. This method can predict motion even if the motion data include human habits. So we decided to use the deep learning based method and apply to predict a club angle. Here is the aim of our research. Aim of our research is to implement a golf swing training with the correct club angle and trajectory every time. This project solves the issue that conventional methods have. To realize such training, we use ungrounded force feedback and motion prediction. As a first step, we correct the club angle using gyroscope. To cope with the delay of gyroscope, we use motion prediction and actuate the gyroscope before the club reaches to the impact point. Using our system, we developed VR golf swing training as an application. Here is a configuration of our system. Our system consists of two main units. One is a prediction unit, and the other is a presentation unit. The prediction unit predicts the club angle on an impact point based on the major club trajectory and club angle. The presentation unit presents the VR golf environment and the force feedback for club angle correction. For the next slides, the speaker is switched to Daichi Saito, who is the other member of this project and implemented the prediction unit.
In the national pilot study, we built a prediction unit, captured the club characteristics using the motion capture system, and sent them to the recurrent neural network we built. The network consists of a LSTM layer to extract the temporal features and the frequency network. The input of the network is 20 frames of 7-dimensional vector, including the club posture in 4D quaternion and the relative 3D position between the club head and the ball. The output of the network is a one-dimensional sine scalar angle, which goes from -90 to 90 degrees. The output is reflected in the real visualization. After several tests on the network, we improved the architecture as shown in this slide. A rest frame estimation network is added to the LSTM layer. The rest frame estimation network predicts the number of the rest frames before impact. And the size of input is changed to 10 frames, and the output keeps the same. We use a motion capture system to measure the position and posture of the club. A special attachment is designed to fix the reflective markers on the golf club so that it doesn't shift during the swing. We took the data from 3 subjects, aged between 23 to 58, 1 female and 2 male, for training the network. All the participants have played golf before, and the time of experience is between 5 to 25. The subjects were only told to stand in a specific position and perform normal swings. As a result, 83 swings, 105 swings, 63 swings were taken from the 3 subjects respectively, which results in a total 251 swings. We compared mean absolute error and standard deviation and mean absolute range error rate of 3 models. The input of 3 models is 10 frames of 7-dimensional vector. Mean absolute range error rate means the average the percentage of difference between the ground truth and the predicted value. In the table, the header per frame stands for the mean error over each frame, whereas the per swing stands for the final error for each swing, where the result of each frame is averaged during the entire swing. For comparison, we use a fully connected multi-layer perceptron as a baseline method, and evaluated the proposed network with without the rest frame estimation network. As a result, LSTM with a rest frame estimation network is the most accurate. Next, we compare the inference time for the prediction in condition with different numbers of input frames. From the table, it's obvious that with a smaller input size, we can obtain faster inference time. Since in our pilot test, the prediction accuracy won't change much with more than 10 input frames. We decided to use 10 frames as input of the system, of which the inference time is 43.65 milliseconds. This data shows real-time predictions during swings. The subjects are told to stand in a specific position to perform swings. The prediction unit will predict the real-time result from 10 frames of the downswing. The predicted club angle is visualized on the bottom display as a red arrow.
Thank you, Daichi. Next, I will introduce the presentation unit. The presentation unit receives the prediction result for the Unity program. This Unity program shows a VR environment to the user through the HMD and operates the gyroscope through control ball. If the predicted result deviates from the correct club angle, the gyroscope presents the torque to correct the angle. Next, I will describe the hardware in the representation unit. I implemented a golf club device with the gyroscope. Gyroscope generates torque by rotating the flywheel using gimbal. Generated torque changes depends on the parameters of the flywheel and gimbal, such as radius, weight, spinning speed of flywheel, and the rotating speed of gimbal, which is represented by the green arrow on the figure. To evaluate the device, we measure the generated torque by gyroscope. We attach a 6-axis force sensor to the gyroscope and measure generated torque with multiple gimbal speed conditions. Center figure shows a graph of sample data. We use maximum torque in the one actuation as measured torque. Right figure shows the final results. Horizontal axis represents commanded value from the system, and the vertical axis represents measured value by the force sensor. Orange line shows theoretical value, and the blue dot shows the measured value. Measured values almost follow the theoretical value. The maximum measured torque in all conditions was 0.65 Nm, which is sufficient to change club posture based on the previous study. This video shows how the gyroscope changes club posture. First, rotate the club to the right intentionally, then starts downswing. When the downswing starts, the device generates torque to the opposite direction. Same operation is conducted in case of left rotation. A video captured by the high-speed camera shows the modification of club posture. By combining the prediction unit and the presentation unit, we developed an application. We selected golf putting as the first application, which is a slow movement in the golf. I will describe how the application works. First, a user wears a head-mounted display and a hold club device. By swinging the club device, the user plays golf by putting in VR. When the downswing starts, the system starts prediction using captured data. Then system sends a predicted angle to the presentation unit. Presentation unit calculates the gimbal angle of the gyroscope to actuate based on the predicted club angle. The system activates the gyroscope with calculated gimbal angle and corrects club angle. Due to the frame rate of the motion capture, we don't use the PID control in club control correction. To match gimbal angle and club rotation angle, we measure the club angles and the multiple gimbal angles. By influence of COVID-19, the participant of this measurement is only me. In the measurement, a participant holds a club device with 2 hands and do nothing. The club angle was measured by a motion capture system. Gimbal angle conditions are every 1 degree in the range of minus 10 degree to plus 10 degree. We use the PID control to control gimbal angle. In each condition, the measurements are conducted 5 times. Figure shows the result of the measurement. The horizontal axis represents the gimbal angle used for the gyroscope, and the vertical axis represents the measured club angle. Gray dot shows the average value of measured club angle in each condition. The result looks linear, and the result of linear approximation also shows linearity. Then we could get the equation to calculate the gimbal angle using club angle. We use this equation to control the device in application. Once the presentation unit receives the predicted angle, the system substitutes it for the equation and gets a gimbal angle for the gyroscope. This is a developed application. Users play putting in the VR environment with club angle correction. Our system implements a golf swing training with a correct club angle every time. In conclusion, we aim to implement golf swing training with the correct club angle and trajectory every time. To implement such training, we adopted ungrounded force feedback and motion prediction. As a first step, we corrected the club angle using gyroscope. To cope with the delay of gyroscope, we use a motion prediction. As an application of our system, we developed a VR putting training with club angle correction. This application realized a golf swing training with the correct club angle every time. Thank you for listening.